Good morning. In this lesson, we're going to talk a little bit about two laws of matter that followed the law of conservation of matter. These two laws, along with the law of conservation of matter, really form the basis of the first atomic theory in the early 1800s. And we're going to take a look at the law of definite proportions. And this is kind of what came from that, okay? This idea that compounds have fixed formulas. We're going to take a look at the law of multiple proportions, which this is the idea that came from that. Two elements, if they combine, even though they're the same two elements, if they combine in a different ratio, they make a different compound. And we're going to apply a little bit of mathematics to calculate percentage composition data for compounds, okay? Now remember, these are laws, which means that they are based on data and experimentation. They are based on facts. And on page 75 in your textbook, they give a longer definition of what is the law of definite proportions, and they kind of put a little background information in it. But what it really boils down to is that compounds have fixed formulas, fixed whole number ratio of elements, okay? Definite proportions, definite ratio of atoms or elements within a compound. It doesn't matter if you have a small drop of water or a big bathtub full of water or a pool full of water. Water is always going to be 2 H's for every 1 O. Compounds have set formulas. So that's the law of definite proportions. The law of multiple proportions, page 76, they really give a more detailed description of that and background of that in your textbook. But what that one boils down to is that you can have the same elements combine, and like if a different mass of the one combines with a fixed ratio of the other in a different whole number ratio, basically you get a different compound. So when you have different ratios of the same elements, you actually have different compounds. Like here are some prime examples. This is carbon monoxide and carbon dioxide, okay? Quite different. Just a different ratio. Instead of 1 to 1, it's 1 to 2. Here's another example. Here's water. This is also a compound that you're pretty familiar with, but I wouldn't want to mistake that one for water and drink a glass of that. Yucky. This is hydrogen peroxide, okay? When you change that ratio of hydrogen to oxygen. So applying a little bit of math to this, we're first going to start out with the law of conservation of matter when we look at this problem and answer how much compound is formed. We know from our previous work, reading this looks like the nitrogen reacts with the hydrogen to make ammonia. And the law of conservation of matter tells us that everything that was present before the reaction has to be equal to all the masses that are present after the reaction. So if we had 28 grams of nitrogen before the reaction and 6 grams of hydrogen, if we just add those together, since ammonia is the only product that it mentions, if we add those together, we can easily figure out the mass of ammonia that has been formed. Now this says determine the percentage of each element in the compound. Now you know that percent means what? Parts out of 100. And so the element is the part, so we'd have the mass of the element, and the whole is the compound, so we'd have the mass of the compound on the bottom. And basically we're setting up a ratio and saying, all right, like if we have 28 grams out of 34, that's the same as x out of 100. We're going to multiply both sides by 100 to give us a formula that helps us to find this percentage. So this is our formula that we're going to use. The percentage is the mass of the element over the mass of the compound. That's just a little random line there, sorry, times 100. I'm going to erase a little bit just so I can have some space to solve my problem. And first I'm going to do the nitrogen, to do each element individually. So that's 28 grams out of 34 grams times 100. And I do that and I get 82.4% nitrogen. Generally, we recommend that you keep the percentage compositions to the 10th. And then the hydrogen, the only number that changes is the number on top because we had 6 grams of hydrogen out of the 34. And when I solve that, I get 17.6% hydrogen. Now you should notice that the percentages add up to 100, right? If you had 3 elements, your 3 percentages should add to 100. Every once in a while, just because of rounding, you might get 99.9 or 100.1. But if you do these problems and you get, for example, 2 percentages and you add them up and they equal 86 or 82 or 120, then you need to go back and check your math because something has certainly gone wrong in the solving of the problem. The other thing is that you do need to pay attention. Like this one says to find each element, so that's why I did them both. Some of the problems that you will come across in the book, they might just ask you to find one of them, like what's the percentage of nitrogen in this compound, in which case you maybe only had to do this problem. Quite often you have to do a law of conservation of mass problem first, and then do your law of definite proportions problem second. Now, in the book, on page 76, there's a couple of problems I'd like you to do, okay? I have a document for you to complete, and make sure you turn it in at the end. If you need help, of course, you should ask, and you can consult your book. Those pages 74, 75, 76 leading up to doing these problems are full of information and examples, and you may ask me as well. So hopefully you are able to explain that compounds have fixed formulas and that 2 elements can make different compounds, even if they're the same elements, as long as they combine in a different ratio. And then work on applying the math to calculating the percentage composition of some compounds. So good luck. Any help you need, remember to just ask.